Okay, so in this short YouTube video, I'm just going to talk a little bit about earthquakes. Okay. So this is plotted on here. We've got the global distribution of earthquakes that occurred between 2000 and 2011, and the colours represent their depth. And you can see, like volcanoes, earthquakes are concentrated in certain areas of the Earth, and these are defined by plate boundaries. And so what we can see from this is that largely plates are devoid of earthquakes, and at their boundaries we have lots of earthquakes. And we can pick out a number of features, so we can pick out mid-ocean ridges in here, and subduction zones, for instance over here in Japan, and the Andes, the subduction zone in here. And also from this, so basically the plates are largely underformed, and we're getting earthquakes at their boundaries. But what is an earthquake? So an earthquake occurs when we get stick-slip type motion. Okay, so where we have no movement on a fault and then sudden movement on a fault. Okay, so but we've got, during the whole process, we've got continued movement of the plates past one another. Okay, so for instance, this strike-slip motion of this fault here in a right lateral fashion. So this block is moving this way, this is moving this way, but this fault through here is locked. But these plates are still moving, so we get elastic build-up of strain in the lithosphere while the fault is locked, and then at some point the fault suddenly, the stress on it becomes critical, or something else happens, some fluid gets released into it, and we get that fault rupturing, and we release the elastic strain energy that was built up in the lithosphere on either side of the fault as elastic waves of energy. Okay? And the amount of energy released is a function of the normal stress that we're putting on this fault, the elasticity of the materials on either side of the fault, the elasticity of the rocks. So if we've got more elastic deformation, there's more stored energy that gets released, and also the frictional properties of this fault plane. If we take that data that I showed you on and we looked at the spatial distribution of earthquakes, we can also take the same data and look at the depth distribution of the earthquakes. So we can see in here that this is the probability. So basically the number of earthquakes divided by the total number of earthquakes in different depth intervals. And we can see that the majority of earthquakes are in the shallow lithosphere, and we get a drop off in the number of earthquakes, and then there's another peak, much smaller peak between in the transition zone. Okay. And if we zoom in on this area in here, we see this kind of relationship between the number of earthquakes and depth. But one important thing to note in here is that this is taking just the raw earthquake data from the USGS website for any earthquake that's above a magnitude 4 between 2000 and 2011. It's just taken them. And in that database there are these big peaks in the number of earthquakes at 10 kilometers and around 30 kilometers depth. And this isn't real. This is just a result of seismologists. If they're uncertain of the depth of an earthquake, they just assign it 10 kilometers or about 32 kilometers if it's thought to be deeper. So these peaks in here are artificial. So to get a better idea of what the distribution of depth distribution of earthquakes are, I've taken this data from another paper in here, and we can see that there's this peak at around 10 kilometers depth, between 10 and 15 kilometers depth, and then we get a gradual decrease in the amount of seismicity, and then in some situations For instance, in India, there is a little bit of a peak at around 35 kilometers, but generally there isn't this peak in the lower crust into the lithospheric mantle. Okay. The majority of earthquakes are concentrated in the first 15 to 20 kilometers of the lithosphere. Another way of looking at earthquakes is thinking about how the magnitude of the earthquake changes and the number of earthquakes. So here we're plotting the number of earthquakes, or the frequency of earthquakes, against the magnitude. And this relationship is called the Gutenberg-Richter relationship. And what you see is for every drop in a magnitude of an earthquake, you get a tenfold decrease in the number of earthquakes. So for instance, if we say we've got about 1,000 magnitude 5 earthquakes, that means we'll have about 100 magnitude 6 earthquakes, about 10 magnitude 7 earthquakes, about 1 magnitude 1 earthquake, and so on downwards. Okay? And this relationship holds true for any given bit of the Earth's crust, but the overall number of earthquakes will change. So, for instance, if we plotted this for the UK, it might be somewhere down here. It'd be like the overall total number of earthquakes would be much lower, and for California, it'd be a bit higher than the UK, but lower than the total number of global earthquakes. And so we can quite easily say, that for any given bit of crust, what the total number of earthquakes of any given magnitude we should get for that area of crust, and we can do that to quite a degree of certainty. The problem comes down at the high magnitude end of the earthquakes, which are very rather infrequently. We get a lot more noise in this data because these are quite rare events. So it can really depend on how long a timescale you're looking at. You can see that there's a higher number of magnitude 9 earthquakes than the Gutenberg-Richter relationship would predict. But it's always a thing that seismologists and earth scientists are always aiming at. Is trying to have a better prediction of earthquakes. And this was brought to a few years ago was brought to the press because two seismologists got convicted of manslaughter in Italy for not giving enough warning of the earthquake in L'Aquila. But luckily 2 years later they won on appeal and didn't get convicted. So whilst seismologists try their best to predict earthquakes, it's inherently very, very difficult to do this. We can give broad ideas of when an earthquake is thing, and we can often say that an earthquake is happening very, very close to when it's going to happen. But other than that, it's very difficult to predict earthquakes. And this is highlighted by probably one of the most predictable earthquakes that we've observed, the Parkfield earthquake. So this is in California, and it occurred every 21 years from the 1850s through to the 1970s, 1960s, and 1960s. And so, and also, if we looked at the seismograms from a station that has been there since the 1920s, you could see that the seismometer signal that was for the 1922, 1933 and 1966 earthquakes were all very similar, which suggests that the crust is rupturing in a very, very similar way over all of those earthquakes. And so that it was thought that the next earthquake after the one in the 60s would be in 1983. plus or minus about 6 years. And so they put a huge amount of instrumentation out, waiting for this earthquake to occur. But it actually didn't occur until 2003, I think. So it was nearly 20 years later than expected. And by this time, the funding had run out for having the seismometers in place. So the Parkfield earthquake is at the end of the creeping section of the San Andreas fault. Okay, so this is a depth section through the San Andreas fault, and you can want some things to notice about this section. So all of these dots are earthquakes on the San Andreas fault, and you can see that there's a sharp cut-off of this seismicity at about 20 kilometres. Okay, and also you can see that the number of earthquakes vary along the length of the San Andreas fault. So we have areas where we have got much fewer earthquakes, an area where there are lots of earthquakes. And this area where there are lots of earthquakes is called a creeping section. And so what happens in here, we have lots and lots of smaller earthquakes in this creeping section. And then over here, in this where there are less earthquakes, there are fewer earthquakes, but they are much higher in magnitude. Okay, so in this locked section in here, we get fewer big earthquakes, but then in the creeping section, we get lots of smaller earthquakes. The fact that we get this cut-off in seismicity at about 20 kilometres tells us that that below this depth, plasticity dominates. So the rock is no longer deforming by fracturing; it's deforming by plastic flow, okay, which relaxes the stresses, so we don't get stresses high enough to induce fracturing. So to summarise, the strength of rocks is dependent on pressure, it's dependent on temperature, and it's dependent on deformation rate. And so we can build up these strength profiles, and the upper 20 kilometres of the lithosphere is dominated by pressure-dependent fracture and frictional strength. And below this, plasticity is the dominant deformation mechanism. And broadly, experiments and depth distribution of earthquakes show the same picture. So we've done experiments to measure the strength of rocks, and we can measure the depth distribution of earthquakes, and they largely show each other, predict each other. And later on in the course, we'll do a practical where we plot the depth distribution of strength from experimental data. So in the next little podcast, I'm going to carry on talking about earthquakes and fault movement senses.